Okay. All right, this is Physics 1C for March 18th. Today we're going to talk about energy and capacitors. We said last time that you can use a capacitor, which, just to remind you what a capacitor is, a capacitor is a device that stores energy between kind of two plates that are separated by a gap. And it does so by charging one plate up with a positive charge and the other plate up with a negative charge. This is usually done by using something like a battery or some type of a voltage source, delta V, like this. And then if you connect them, it will charge up your capacitor. The capacitor will then hold that charge unless you give it a path along which the charges can kind of annihilate. And we said that the capacitor has a capacitance C, and that capacitance was defined as the amount of charge the capacitor can hold divided by the potential difference between the plates. So what happens is that the bigger the value of the potential difference, the more charge that you can actually pack on the plates, but the ratio between those two things, that's your capacitance. Now, after you store this energy up, you can release it and have it do work for you in some way. And like I said, some examples of this are flash photography. When a flash bulb goes off, quite commonly it's coming from energy stored in a capacitor. And capacitors can also be used for timing in circuits, something we're going to talk more about in the next chapter when we learn about resistors, because you need both a resistor and a capacitor. And they can do all sorts of other things. They can be used to tune radios, so you can tune into a Wi-Fi network that you want to, or you can tune into a FM radio station or something like that, if anybody still listens to those kind of things. So, yeah, capacitors are they're pretty interesting. And today we're going to talk about some of the aspects of the energy in a capacitor. The very last thing that we did at the end of yesterday's class was we derived this idea that you could calculate the amount of energy that's stored in a capacitor, and we use the symbol U for potential energy, and then a subscript C to represent that we're talking about a capacitor. By doing this, if you take the amount of charge that's on the capacitor, you square it, and then you divide by 2 times the capacitance, that will give you the energy that's stored in the capacitor. There are other ways to do this, because you can use this equation right here to rewrite this. And what are those things? I guess we could do them. So for example, if we plug in that Q is equal to C times delta V, then I think this would become 1/2 C delta V squared. And then if we were instead to replace the C, I think what we would get is 1/2 Q times delta V, I believe. I think those are correct. Those look like what I told you last time? You could check.
Yeah, they're the same.
Those are the same? Okay, good. I just kind of was doing that in my head. Wasn't sure. All right, so that's what we learned last time. We did some problems where we combined capacitors together. And today we're going to start off by solving this problem right here. I think this is from university physics. A lot of the examples we do aren't, but this one is. So in this problem, we have this system of 2 capacitors right here, C1 and C2. And it says 2 capacitors, C1 and C2, where C1 is greater than C2, are charged to the same initial potential difference, delta VI. The charged capacitors are removed from the battery, and their plates are connected with opposite polarities. Okay, so each one of these is given the same initial potential difference. So this one is charged to some potential difference delta V sub I. This one is charged to some potential difference delta V sub I. They're both the same amount. It could be, remember, this is just a voltage. This could be like 9 volts if it confuses you to look at these subscripts and symbols and stuff. They're both charged to the same number, maybe 9 volts or something like that. And then they are connected. Oh, then it says the charged capacitors are removed from the battery. The thing about capacitors is they will retain their charge even if there's not a battery attached to them, because there's really nowhere for the charges to go. There's a gap between these plates, and the charges can't really jump across the plates. Okay, so they're connected with opposite polarity, so the negative on the left side of 2 and the positive on the left side of 1, like this. They're connected in this system with these switches right here. All right. And the switches are initially open. It says then the switches are closed, as in the picture on the right. As a result of that, when you close the switches, the charges from the positive side of this one over here are going to be able to then travel along this path right here, and some of them will annihilate some of the negative charges on the left plate over here. Right? Now I'll just ask this question so we can kind of understand this as we go. If I charge both of these capacitors to the same potential difference, and I tell you that C1 is greater than C2, which one is going to have more charge?
Will be C1.
Yeah. So would you all agree that this has to be true? Q1i has to be equal to has to be greater than Q2i? Yeah. Okay. So as a result, if there is more positive charge on this plate, let's say it's positive 10 coulombs, for example, than there is on the negative plate down here. Let's say it's like negative 5 coulombs. So if this is 10 coulombs and this is negative 5 coulombs, then does it make sense that after we close the switch and we allow charges to flow between these plates, that both plates would then suddenly become positive?
Yep.
Okay, good. All right, so that's what's happening, basically. Now, the charges are not allowed to flow any farther because A and B are not connected to anything. They're just an open point in the circuit. So really, only the left-hand side of the plates can communicate, and only the right-hand side of the plates can communicate. Okay, they can't communicate across here. Okay. All right, so our goal is to find the final potential difference delta VF between points A and B after the switches are closed. Okay. And I'll just say that because they're in parallel, what do we know about the final potential difference and how they're going to be related to each other?
It'd be the same.
They're the same, right? Okay. So it says to find the final potential difference between points A and B, but that is the same thing as finding the potential difference on capacitor 1 or capacitor 2, because one of the things we learned last time is when you have capacitors in parallel, as these are, they have the same potential difference. That's, in fact, going to be what causes them to come to equilibrium, right? That's going to be what causes them to come to equilibrium. Charges will basically flow until the potential difference is the same, because at that point, there's no more kind of energy to flow for the charges. All right, so that's the first thing we want to do, is figure out what is this equal to. All right. So in order to do that, we're going to start off with a conservation law. We know that electric charge is a conserved quantity. You can't create or destroy it. So as a result, we're going to look at conservation of charge on the, we'll do the left plates. Okay. So initially, on the left plates, so we're just looking at this plate, and we're looking at this plate. Initially, the total amount of charge on the left plate is going to be Q1 initial plus Q2 initial. Except that Q2 initial is negative, so we'll do Q1i minus Q2i. All right. After the switches are closed and an equilibrium has been established, the total amount of charge on the left plates is going to be Q1F plus Q2F. Does that statement make sense to you all?
Not really.
All right. Okay, let's make this just a little bit smaller now. to work with here. Okay. Here, let's move this over. That way we can kind of work from left to right on the screen here without moving too much. All right, so because of the relationship between the charge, the potential difference, and the capacitance, which is Q is equal to C times delta V, right? That's our general equation that we know about capacitors. We can say that Q1I should be equal to the capacitance of Q1, which is C1, multiplied by the potential difference, which is delta V sub I. For Q2, it'll be C2, and then delta VI, the initial potential difference. For Q1F, it'll be C1 times delta VF. And for Q2F, it'll be C2 times delta VF, right? Because delta VF and C2 are what you have down here, delta VF and C1 are here, and so on and so forth. We could then factor these out. So we'll have C1 minus C2 times delta V initial is equal to C1 plus C2 times delta V final. And then I guess there's enough room down here to write this. So the final result then is going to be, and this is all part A, delta V final is going to be equal to C1 plus C2 divided by C1 minus C2. Oh, we're not full screen. That explains why I feel like I had less room than I thought I would. That times delta V initial. And that's the answer to the first part.
Wouldn't you divide by C1 plus C2?
Yeah, I guess I mixed them up, didn't I? Sorry about that. We're finding this one, so we divide by this term. Exactly. Thank you. There we go. Now, I think looking at this kind of is hard to look at to understand what it's really saying. But what it's saying is actually pretty simple. So let's just pick some numbers so we can get an idea of what it means. Okay. So if we were to let delta V initial be equal to, let's say, 10 volts, and we let C1 be equal to, we have to have C1 greater than C2, right? So let's just pick some simple numbers like 2 microfarads for C1, and we'll make C2 equal to 1 microfarad. Given those values, what would delta V final be?
Isn't it 10 over 3?
Yeah, so like 3.33 volts, right? So if you start with 10 volts and I give you these two capacitances, the answer is it's about a third of the voltage that you have left over, right? Okay, that's because in the numerator you're doing 2 minus 1, which is 1, divided by 2 plus 1, which is 3. Okay. All right, let's do part B. In part B, it says, find the total energy stored in the capacitors before and after the switches are closed, and also the ratio of the final energy to the initial energy. All right. So we want the energy stored in the capacitors before and after. So we'll say this, U1 initial is going to be equal to, how do we want to do it? I guess we want to use this, I think we want to use the CV squared method probably. We're going to want to use this one, 1/2 CV squared, I think is the one we want to use for this one, because we already have a lot of information about delta V and C. So we'll write that U1 initial is going to be 1/2 C1 times delta V initial squared. Then U2 initial will be 1/2 C2 times delta V initial squared. And we'll just go through and fill the rest of this out. U1 final will be 1/2 C1 delta V final squared. U2 final is going to be 1/2 C1 delta V final squared. And now it says we want to find total energy, right? So the total initial energy, U initial, is going to be equal to the sum of these two terms, this one and this one. They both have delta V initial in common, so when we sum them, we're going to get 1/2 C1 plus C2 multiplied by delta V initial squared. And then when we do U final, we're going to get 1/2 C1 plus C2 delta V final squared. But we know what delta V final is. So we can plug that in here. But before I do that, I just want to stop for a second and make sure everyone's still following along. Is everyone following along still? Anyone have any questions? Oh, thank you. Yep, that should be a 2 right there. Appreciate that. Okay, so now what we want to do is we want to... I'll wait a second because people are typing. Okay, so now what we want to do is to plug in delta V final into the second expression right here. Let's switch colors. So U final is going to be 1/2 delta V final is equal to C1 minus C2 over C1 plus C2. But we have to square it. And when we square it, some things are going to cancel out here. C1 plus C2 is going to cancel out with one of these. Am I doing this right? Doesn't look like I made it. Doesn't look like I made it. Oh, the ratios were it. Okay. All right, never mind. I'm thinking like too many steps ahead. All right, so C1 plus C2 cancels out with this. We get C1 minus C2 squared. And then there'll be one more C1 plus C2 in the denominator. It's not squared, like this. And all of that's times delta V initial. So now we've technically solved half of it. It said, find the total energy stored in the capacitors before and after the switches are closed. So we did that. This is the initial. And this is the final after the switches are closed. And now we want to find the ratio. We're going to do U final over U initial. Doesn't really matter which ratio we do. Yep. So on the numerator, we're going to have okay, that's U final, and then U initial is this one. Sorry, the delta VI's are supposed to be squared. Doesn't matter too much because they're going to cancel out. So now we can reduce this. All that stuff cancels. And our final result is C1 minus C2 That's squared. But now we're dividing by C1 plus C2, and it's in the denominator down here, so those will get squared too. So that is our answer. The ratio is C1 minus C2 divided by C1 plus C2. Which, if we were to use the numbers that we have here, C1 equal to 2 and C2 equal to 1, what would this be equal to?
1/9.
1/9. That's right. So let's talk about this and kind of what it means. So we started this problem by using a conservation law. We used conservation of charge because we knew that there wasn't really any way for the charge to leak off the plates in our ideal system right here. We're also using wires, and I didn't mention this, but we're using wires that are what I would call superconductors, in the sense that they're not going to dissipate energy in any way. But nonetheless, we take the ratio of the energy of our system before we close the switches and after we close the switches, we see that we've kind of lost a lot of energy, right? Oh, the answer's blocked, isn't it? Yeah, okay. Sorry about that. Let me move it over a little bit. Thank you. Is that better? Should be able to see it there. Okay, let's back up a second. So we started off with conservation of charge, right? And we used that conservation law to show what the ratio or the final potential difference was, right? And then we used that information, and we went through and we calculated what the energies stored in the capacitors are. And we found that, well, what's happened to the energy? A lot of it's gone, right? If the ratio is 1 to 9, then that's like saying we started off with 9 joules of energy, and now we have 1 joule of energy, right? To put that into some kind of perspective, that would be like, I think for energy, a good comparison is just always food. So it would be like it'd be like you took a Snickers bar and you put it on the table, and you left the room, and you came back, and there was only 1/9 of it left, or something like that, basically. The final answer does not have. That's a good question. The final answer doesn't have units because it's a ratio. The units completely cancel out when you do ratios, right? So yeah, so where would all of this energy have gone? Now, in the next chapter, we're going to talk about resistance. And resistance is the way in which a wire can cause electrical energy to get turned into thermal energy, okay? But that's only if the wire has any appreciable amount of resistance to electrical flow. And in this problem, we didn't say anything about that. So that's not what's happening. We're not losing energy to friction or heat. If you compare this to something that you do in Physics 1A, for example, in Physics 1A, you'll do these problems all the time. Like, for example, the one that comes to mind is inelastic collisions. Do you all remember those problems where you'll have, like, a bullet, it's fired into, like, a block, and then the block basically, absorbs the bullet, and then it starts to move? Do you all remember those kind of problems?
Yeah.
And like the ballistic pendulum lab is an example of this. Now, I don't know if any of you did the ballistic pendulum lab because we haven't done labs for like 3 semesters now. But when you do that problem, really commonly, one of the things that you'll calculate is exactly what we did here. What is the ratio of the final energy to the initial energy, specifically kinetic energy, right? And you find out that you lose a lot of energy in those kind of problems, right? But you know why. Usually it's because of friction. Usually it's because of a transformation of mechanical energy into thermal energy in the form of, heat. The block warms up somehow. The bullet has to actually burrow into the block, and that's where all the friction's coming from, and that's a lot of dissipation of energy as heat, right? Okay. So you've seen systems where there was an apparent loss of energy, but you knew why it lost energy, right? Take a box sliding on a flat surface. You push it, it has kinetic energy. It slows down due to friction. And you say, where did the kinetic energy go? And, the answer is that It was kind of transferred into the molecules of the table. All that kind of stuff. You have an understanding of when it makes sense, right? So we want to gain an understanding in this situation too of where that energy goes. And unfortunately, unlike mechanics in this case, the answer is not heat. Often that's what the answer is: light, heat, sound. That's usually what the answer of where the energy goes is. But that's not the case here. Does anyone know what happens to the energy? Before I even ask that question, would you all agree it's kind of strange? We don't usually see a lot of systems where energy is lost. We usually just think, conservation of energy is this fundamental principle in physics. It's always true, or whatever. So it is weird, right, that we're losing energy. We're not losing any charges, but somehow we're losing energy. So, where do you think it went?
I don't know, but does it have something to do with the plate's charge being flipped from when the switch is on and off?
Maybe. May have something to do with that. The charge is flipping. May have something to do with that. Prince Ali saying, isn't energy having something to do with heat? Yes, a lot of times that's usually what happens, Prince Ali, but unfortunately that's not what's happening in this case. We're using wires that are what are called superconducting wires. Okay, so they don't dissipate any energy. We'll know more about what that means in the next chapter, I guess, but it's not heat.
Does it work?
It's not work. I don't know that anyone is automatically going to know the answer. I'm just kind of asking for you to speculate. Like, literally just completely speculate where you think it might have gone. If you don't know, it's fine. I'm just kind of curious to know, like, what you would think would happen here.
Did it go into, like, some type of magnetic field?
Possibly. That's on the right track, yeah.
Because, like, we don't lose any charges because it travels along the wire. It doesn't turn into heat.
Mm-hmm. Right. Okay, so two things were said. One was that, does it have something to do with the fact that the charges annihilated each other? The positive charges came out down here and kind of, annihilate's the wrong word, but kind of canceled each other out. The positive charges basically filled in the negative charges down here. So there's a motion of charge, right? And you said maybe it has something to do with magnetic fields. Okay. Any other ideas? Both of those are on the right track. You can feel free to get extremely speculative, Think about all the things that you've learned in your science classes or from watching movies or from watching YouTube videos or maybe even something you may have learned like in 6th grade science or something like that. I don't know. Is there any kind of phenomenon that is related to electricity that could cause energy to come out of the system?
Some type of discharge?
Discharge? Well, this
Like
is a kind of... What were you thinking? Go ahead.
No, I was like saying like when you see like like when you get
spark?
zapped or something, yeah.
Yeah. I don't think there's going to be any sparks that are occurring here. Because if there were... So to have a spark, you can't have a wire. If you have a wire like this, you're probably not going to get any sparks. You would see sparks across gaps, basically, right? You think about when you shock someone, there has to be like kind of a gap across which the spark can travel, and the spark has to kind of travel through like air or something like that, right? But because the charges are completely contained within the wires, that's not it. But that's a good guess though. It's certainly thinking along the right strategy. Any ideas? Maybe this doesn't bother you as much as it bothers me. I don't know when people first discovered this problem. I really don't. I don't even know if people really did discover this problem as they were developing the history of electricity. But we know about it now. And it's a nice way to introduce something that's going to come up later on. Any other ideas? How could energy get out of the system? How could it possibly get out? And it has to be based on something that you've heard of before, too. You have to, like, I wouldn't be asking this if it wasn't possible for you to figure it out. Just trying to see if you can make the connection. How could you possibly get energy out of this system if you're not going to use heat and you're not going to use, yeah. How could you get energy out of the system? Think of all the ways that energy can be transferred. Light. That's the right answer, Jacqueline. That's exactly right.
It's light.
Yeah. So it's not light that we would see. And when you said the spark thing, that's actually kind of on the right track, because sparks obviously create light, right?
It was related to the motion of the charges.
Yes,
that
exactly.
creates some type of light. Okay.
That's exactly right, yeah. When these charges move, so all of you are kind of on the right track when you said something about, is it about the motion of charges and annihilating each other? Someone said that, and then when you said magnetic fields are connected to light as well. So some magnetic fields are actually produced in this process. And then, yeah, it's light. So when you learn about, this is why I said you might have learned about it like in 6th grade, is because in like early science classes, you kind of start talking about energy transfers, and you learn about how energy can be transferred through like heat conduction, but it can also be transferred through like radiation, right? There's these 3 methods by which heat is transferred, or energy. There's conduction, convection, and radiation. Radiation is light, basically, right? And what you end up learning is that when you have charged particles that accelerate, they emanate waves. The acceleration of charged particles will cause waves to emanate out from the system, and we call those waves electromagnetic waves or electromagnetic radiation, and that's what's going on here. And it's a huge amount of energy that's lost, and it would probably not even be very detectable, because it might not be light in the visible spectrum. It might be like microwave radiation. It might be like radio waves. You know, we might not be able to visibly see it with our eyes, but we know that the energy must have left the system somehow. And later on, we're going to learn exactly how you can produce this. And the first experiment that was done to prove that light was an electromagnetic phenomenon was done by a guy named Heinrich Hertz, and his experimental setup was very similar to this. He was basically just using 2 different circuits that had little gaps, basically 2 big balls that were made of metal. And what he would do is he would basically induce a shock between the 2 of them over and over again, and prove that you could actually transmit waves across the room and have them be picked up. He basically constructed the first radio transmitter and radio receiver, in a way, by using a system almost exactly like this, except that he forced this process to occur constantly. He basically forced the plates to basically charge up and then discharge, charge, discharge, charge, discharge, charge, discharge, and that caused waves to go across the room, and then that basically he could detect how long he could detect their wavelengths and prove that they moved at the speed of light. So energy can also travel at the speed of light, or is it light? Both. Yeah. Energy can travel at the speed of light in the form of this type of radiation that we're describing. Yes, Prince Ali. If that answers your question. In the case of this particular type of energy, which is light energy, it definitely travels at the speed of light. It travels at the speed of light. And what we're going to learn is that light is merely just a kind of a fluctuation of the electric field. And so in problems like this, what's happening is that the electric field is changing so rapidly that it propagates light waves. Just like ripples in a pond, you know? Just like a disruption in the electric field, it causes ripples to go out that can be detected. And that's what your eyeballs do. We're all constantly detecting these ripples of the electric field. Okay. So, I'm impressed you got that, by the way, Jacqueline, because people never get this answer. I usually just sit here and wait and wait and wait. Normally I don't wait long enough, maybe. Maybe I just had to wait a little longer, but good job on figuring that out. That's really good. Does anyone have any questions?
I guess it's just weird that it's undetectable light to me.
And no,
'Cause
no,
it's,
it's not undetectable just by our eyes. Does that make
Hmm.
sense?
yeah, okay, that makes sense.
If we got like a radio tuner, you'd hear it probably. You know, it might show up as like static on your radio device or something like that, or you could probably tune in and actually specifically pick it up.
Imagine the type of like wavelength that's produced by that is based upon how fast it travels, right?
Yeah, I think that's right. How fast the kind of acceleration of the particles is going to occur at.
Mm-hmm.
Yeah, exactly. Is it true that even when we reach the speed of light, we still can't see it? Can't see it? What do you mean by can't see it? Can't see it. So, first of all, as far as we know, you can't really travel at light speed unless you already were traveling at a light speed. Because we believe it would take an infinite amount of energy to ever get a vessel up to light speed. But you can travel really close to light speed if you want to. And, what do you mean by can't see it? What is the it?
Can't see light. Or like light in general.
You would still be able to see things.
Okay.
You would still be able to see things. There are some things that happen when you approach the speed of light, though, that are strange. Your view of the universe around you would change a little bit, I think. Things would start to look kind of squished, like almost like looking in a mirror that kind of stretches your body to look really thin. If you've ever been to if you ever looked at like a funhouse mirror or something like that, where you look in the mirror and you look like really tall and skinny, that would kind of be like what you would see. Is that people are, I mean, if you're moving at the speed of light, you're moving so fast that it's hard to see much of anything. But anything that you could see should appear to be kind of squished. And then, in addition to that, time starts to move more slowly for you compared to other people. There's all sorts of weird things. And I say all this stuff, but it's not like I've ever traveled at light speed. You know, I can talk about theoretically what it should look like, but I have no idea what it really looks like, if you know what I mean. It would definitely look very different, though. I say that. It might not look different at all. But yeah, we can't really reach light speed, unfortunately. Although there have been a lot of news articles lately about kind of new breakthroughs in our understanding of warp field technology, where people think they can actually construct a warp drive. So, who knows? There is a way to kind of break that light barrier, which is you need to warp space in some way. The only thing is we think it takes a huge amount of energy to do so. And, that's not to say we won't figure out how to do it. And honestly, I really hope we do, because we're currently living in a very kind of sad time in terms of stellar exploration. Because the only thing we can really ever hope to explore in our lifetimes is our solar system. The nearest stars to us are extremely far away. The closest star is about 3 light years. So even if you were traveling at the speed of light, it would still take 3 years to get there, which is, that's not that big of a deal, right? I mean, think about explorers in the 13 and 1400s. They went on voyages that probably took years, right? But the problem is that that's if you're traveling at light speed. And in reality, we'd be lucky if we could get to 10% light speed, which would mean the journey would take 30 years. So you'd have to have people on, and then that's to get there. So you can't really come home, right? So we really need something like warp drive technology to actually start exploring our galaxy. Otherwise, we're going to be stuck with exploring our galaxy with our telescopes, or possibly exploring the galaxy with robots that can self-replicate. Anyway, this is all kind of very interesting stuff, but a little off topic. It's not really off topic, though, because it's still physics. And I'm always happy to talk about all that kind of stuff. Okay. Anyone have any other questions before we move on? We're almost done, so there's not much left that we have to do. So if there's any other questions you all have about this, like, feel free to ask. Okay, we're next going to talk about the energy of the electric fields. Okay, so in order to do this, we're going to use a capacitor. We've already said that you can store energy in a capacitor. So what we're going to do is we're going to actually try to connect the energy of the capacitor to the energy that the electric field itself stores. And we want to know, how is the energy of the electric field related to the electric field size? So I think it makes sense to presume that the bigger that an electric field is, the more energy there would be in that region of space. And that's basically what we want to prove. All right, so we start off with capacitor plates. And we're going to take two capacitor plates, and we're going to separate them by a distance d. Try to make them parallel if I can. So we have two capacitor plates. Each one is going to have an area that we say is A, and they're going to be separated by a distance d. And they'll be charged, of course. So let's say the left one is positive, and the right one is negative. We know that there are electric field lines that are going to exist between these two that kind of look like this. I was trying to click the green one, but it didn't work. Green. There's going to be electric field lines between these plates that look something like this. And then we need one other thing. We need to connect this all up to a battery. So positive side here, negative side here. And our battery is going to have a potential difference that we say is delta V. Okay. All right, so we'll need a few equations to actually find how the energy is related to the size of the electric fields. So some of them will be, let's see, which ones do we want? We probably want, well, any of these will work. So U sub C is the charge squared over 2C. We need the definition of capacitance for a parallel plate capacitor, which is the capacitance is equal to epsilon naught times A divided by D. We're also going to need the definition of the electric fields and how it relates to the potential difference, which is the potential difference is going to be equal to the electric field times the distance between the plates. I think that's it. And actually, now that I look at what we have, we probably want to use this definition. U sub C is equal to 1/2 C times delta V squared. I think that's the one we want. That's going to be a little easier to work with. And then we might need the other equation, which is Q equal to C delta V. I don't know if we'll need this or not. So let's put this all together. So we have capacitance is epsilon naught A over D. Yeah, this is a really short proof now that I think about it. Delta V is ED, but we need to square it. When we do that, one of these D's is going to cancel. And what we're left with is the energy. I'm going to just call it the energy now, because we're going to kind of try to generalize this beyond capacitors. The answer we get here is going to have nothing to do with capacitance. So we have 1/2 epsilon naught, which is the permittivity of free space. Again, this constant represents the resistance that space itself places on the development of electric fields. So epsilon naught multiplied by the electric field squared, and then what's left over is A times D. Now, A is the area of the plates, and D is the distance between the plates. So what does A times D represent?
Volume.
Volume.
Volume. Yeah.
That gap between them, right?
Yeah, so AD is basically equal to, oops. So that's equal to volume, and it's the volume just of the capacitor, the volume contained within the capacitor. So what we're going to do is we're going to divide it to the left-hand side. So U divided by volume, U is again energy, is equal to 1/2 epsilon naught E squared. And then I'm going to use the symbol that most books use, which is a lowercase u. I know it looks exactly like the uppercase U in my handwriting, but this is a lowercase u. And we'll put a little E subscript on there, and this is our answer, actually. This is going to represent the energy per unit volume for the electric fields. We call this the electric field energy density. Is that what we call it? The energy density of the electric field might be a better way to put it. So this is the energy density as I started looking at my second monitor as I was writing to see if I was going to go off the screen, and it got really messy. Energy density of the electric fields. So what this means is that electric fields themselves actually carry energy. And how much energy do they carry? Well, they carry an amount of energy, U sub E, that's equal to 1/2 epsilon naught E squared per unit volume. So anywhere in space that you have electric fields, there's energy there, okay? And that's because, if any particle were to come along that was charged, it would feel the force. So the energy per unit volume is equal to the electric field squared. And that's it. That's what it is. Commonly in experiments, at least the experiments that I was doing when I was in grad school, we would often say that it's a lot easier to measure electric field squared than it is to measure electric field itself. If that makes any sense. This quantity is much easier to measure than the electric field itself, because to measure the electric field, usually what you have to do is you have to go and measure a bunch of delta V's, a bunch of potential differences, and then kind of map out your electric field. But measuring E squared is much easier because it's directly related to energy. So there we go. And that's kind of the end of today's lesson. Anyone have any questions? I guess one other thing to say about this is that since the air around us has energy, yeah, and it gets transported around all the time, what I was going to say is that since the electric field carries energy, or has energy within it, that means that energy can be transported around, right? And that's basically what light is, as the energy of the field itself gets transported around.
And magnetism can affect that, right? It can affect like the discrepancy of energy, right? Okay.
Yeah, exactly. In fact, what we're going to learn later on is with magnetism, we're going to learn that the energy of the magnetic field per unit volume is going to be 1/2 mu naught. So mu naught is kind of like epsilon naught, but just for so E for electricity, M for magnetism. This represents the resistance that space itself places to the production of magnetic fields. And guess what? We use B for magnetic fields, and that's what the energy of the magnetic field looks like. And one of the very last things that we're going to do in this class is we're going to put those two concepts together, and we're going to show exactly how much energy is carried by light. And we'll calculate, for example, how much energy is the sun depositing on us, every day. And we'll then calculate the electric field of the sun, and well, not exactly the electric field of the sun, but the electric field of the light waves that the sun's producing as they come to Earth. So yeah, but you're absolutely right, Prince Ali, that it's connected to the magnetic field, because these disruptions within the electric field wouldn't really be able to propagate very far if it wasn't for the magnetic field. We're going to learn that fluctuations within the electric field create fluctuations within a magnetic field that cause the thing that we call light to be able to propagate extremely long distances. So, yep. Anyone else have any other questions, comments? What about light pollution? Yeah, what about light pollution? What does light pollution mean? So light pollution, my experience with it is that here in Los Angeles, I think there's more than one definition of what that means, probably, but here in LA, when we look at the night sky, we can't really see that many stars. Whether you know it or not, if you were to go out into the desert, I hope that you've all done this at some point in time. If you've never left the city, then maybe you haven't, and that's fine. But if you go out into the desert and you look up at the night sky, if you get far enough away from cities, you'll notice that there are just, I don't know what the right number is, billions and billions of stars that we can see. And you can also kind of see a streak through the sky that's called the Milky Way and stuff like that. But in the city, you can't see as many. You can only see the very brightest stars at nighttime. And that's just because there's just so much light that's produced by the city itself. And so it makes it really hard for us to see light coming from distant stars, because the light from distant stars is really faint, and the light that's close to us that's being produced by our cities is really bright, basically, right? So our eyes are really only going to be able to detect whatever the thing that's the brightest is. So, yeah. Is that what you meant by light pollution? Or did you mean something else? I think there's more than one. Go ahead.
It's also called ambient light.
Ambient light? Sure. Wait, ambient light from what? Just from cities?
Yeah.
Yeah, basically the same thing.
Okay, that's what I thought.
But light doesn't pollute in the same way as like air and water can get polluted, right? It's not the same kind of. It's just more about I mean, for what I'm thinking about, it really just has an effect on observing the cosmos, I think. It also, I guess, it has a negative effect on like young students being excited about astronomy, I guess. One thing that's really hard for us here in LA is to find people to come teach astronomy at El Camino. And I wonder if maybe it's because if you grow up in Los Angeles, you don't have nearly as much of a connection with the stars as you do if you grow up in the country. I mean, I grew up in a pretty small town in Oklahoma, and I mean, every night I would go out on the deck with my dad, and we would look at constellations, and you know, I mean, I think I probably got excited about science and got excited about astronomy and studying that because I could just go outside and see it. You know, I could go outside and I could see Venus, and I could see. I mean, you can see Venus and you can see the planets in LA too, but you know. I guess that's one negative effect it has on, like, keeping people curious and wanting to know more, maybe. Because if you look up in the sky and you only see a few dots of light, they don't really mean as much to you. In fact, most of the dots of light you see in LA are probably they're probably airplanes. All right, well, I'm gonna stick around. Interesting. You weren't really taught anything about astronomy in school, so you can see why a lot of people are interested. That's really interesting. Yeah, I'm trying to think. I don't know that I learned anything about astronomy in school either until college, I guess.
I'm taking an Astro 20 class currently right now. It's actually really fun.
Cool. Are you doing that with Kadakia?
No, I'll take a Robert.
Roberts. Okay, cool. Nice.
And so it's just the class. I know you get. I just took it for fun. I know it sounds weird, but I just took it for fun because I'm an aerospace engineering major, and so I took Professor Hacking for 1A, and he said that I recommend you taking an Astro 20 class. Or him himself, he was an astronomist himself, so he was like, you should take it. It's fun, and so far it's been interesting. You really get to learn a lot more.
That's cool. I'm glad to hear you're liking that. That's really good. Yeah, I think everybody should take astronomy. I think
that's why I was kind of asking. Sorry to interrupt you, but that's why I was asking about the light questions at the speed of light and all that stuff.
Oh yeah. I'll tell you what. That's a really good question to ask Dr. Hacking. What does it look like when we reach the speed of light? I don't know that he's going to know, but he's certainly he might have a better perspective on it. But yeah, I really think everybody should take astronomy. I took astronomy in college and I loved it. I took it for like multiple semesters. All right, I'm going to go ahead and stop this stream right now, but